to show you how to represent the domain and range of a particular graph. So let's start out with a graph that looks like, let's put a dot here. Let's make a parabola. Alright, so if I want to find the domain and express it in interval notation, I want to think about where the x values lie on this curve. Okay, so we can see that this arrowhead here means that you're getting x values going all the way to positive infinity in this direction and all the way to negative infinity in the other direction, the negative direction. Alright, so there are no x values that we don't have. In other words, there's no holes, there's no limitations on where this graph goes in the x direction. So the way we represent that is negative infinity to positive infinity round brackets. So the understanding is that that means all real numbers. All right, now let's look at the range. Okay, so the range is everything, all points above that line there. There's nothing below that line. Okay, so it's everything above that line. All right, so what we do is we say we're starting at a particular value of, let's see, 1, 2, 3, 4, negative 4, and we're going up all the way to infinity, round bracket. Okay, so that's how we would express the range of this graph. Let's try another one. Okay, so here I've got a square root function with the hole at the leftmost point. So if I want to express my domain, I'm talking about all x values that start here and go to positive infinity. However, I have a hole at the starting point. So we're going to say starting point x negative 5 all the way to infinity. Okay, so that's my domain. And then for the range, I'm starting lowest y value and I'm going to infinity in the y direction. So once again, there's a hole, so I'm going to start at, let's see, the y value is 4. Highest y value would be positive infinity. So that's how you would do it for that graph. Let's do one more graph. All right, so this one's a little different. This is a graph of a rational function, and so we study these functions a lot in pre-calculus and also in calculus. So these have vertical asymptotes. So that dotted line there, right here, is what we call a vertical asymptote. All right, so we're going to get into this quite a bit in the future. But for now, we can see that there is a problem right there. The graph is this piece, and the graph is this piece. But this value of 1, 2, 3, 4 is not on the graph. Okay, so we've got a split domain here. So the way you represent a split domain is you always go from left to right. So as far as this piece goes, right here, this is the leftmost point in the x direction here, which is negative infinity, round bracket. All right? So then we travel along the graph, and we get to the point where we've got a split in the graph here at 4. So I end that piece. I put a 4 here with a round bracket because it never actually gets to 4. It stops there. All right, so then I use this U, all right, because I got a 2-piece domain here, so that's my OR symbol in set notation. All right, now I'm over to this piece of the graph over here. All right, so that one picks up at 4 again, and it goes to positive infinity. All right, so this business right here is your split. So that's how you represent a split like that with a vertical, where you would have, for instance, a vertical asymptote. All right, and then the other times you might have a split is, let me just go ahead and put that right on this same graph. Let's say you had a hole in a line which otherwise was continuous. Okay, so you've got a split right there at 4 as well. So this domain here also represents a graph like this, where you've got a split here with a hole. You go from negative infinity to 4, and then you got this whole business going on, and then you take up again 4 to infinity to represent this piece of it. So when you have a hole or a vertical asymptote, you've got to represent it with this split right here. All right, now let's get that off of here. Now let's talk about the range here. All right, so we got a split here as well. So we got a split here, we got a split in the Y. All right, so if we're talking about the range, we go lowest to highest. All right, so here's lowest point, and you go up here, and then you hit this problem area here at Y is equal to 0. So we start at negative infinity. Okay, we're on the graph until we hit 0. So that means negative infinity to 0, then we split. All right, so then we take up, we're on this graph on the other side of 0. And then we go all the way to infinity in the Y direction. Okay? So that's your range. Now, that's not the only graph that could potentially have that range. Like if you have a line with the split at 0, for instance, all right, that's got the same range. So it could apply to multiple scenarios. So what if you're given an equation and you're asked to determine what the domain and the range are? Let's just first talk about the domain. All right, so when you're given a polynomial, this is a polynomial, this is a polynomial. Polynomial, as we know, is just a string of positive powers of x with coefficients in front, and then either positive or negative signs in between the terms. So polynomial, polynomial. Now, when we're talking about domain, there aren't any domain restrictions for polynomials. All right, so one way to represent this is in interval notation. So we can say that the domain is negative infinity to positive infinity. Okay, that's for a polynomial. There are no x's that are excluded from the domain. This is also a polynomial. So all real numbers for the first two. Okay, now when we get down to this third one here, if x is 2, we've got 2 minus 2 equals 0 in the denominator here. So 2 is a problem number. If x is equal to 2, then I've got an undefined denominator. I've got an undefined. I've got 1 over 0 undefined. All right, so what we say here is you're going to leave 2 out. Okay, so we say that by domain is going to go from negative infinity to 2. Then there's going to be a hole. We're going to represent that with this split here. You put your u in, and then to infinity on the other end. So this here, in interval notation, represents your split, where x cannot be 2. All right. Now, on the fourth one, we've got a square root function, and we know that underneath you cannot have a negative number. So your 3x minus 2 has got to be greater than or equal to 0. So that means 3x has got to be greater than or equal to 2x has got to be greater than or equal to 2/3. All right. So let's go ahead. Let me just make a quick sketch here for you of what this guy would look like. So your dot, let's say this is 1, this is 2. So your dot is going to be at 2/3, and your square root function is going to be shaped like this. All right? So that's your square root function. So if I want to represent my domain, I'm going to say my domain starts at 2/3 square bracket and goes to positive infinity. Arrowhead represents positive infinity. All right? So we're going from 2/3 to infinity. All right? So let's go ahead and do the range here as well, since I've got the graph here. So the range is going to be all possible y values, starting at 0. This is my lowest y value, going to infinity. So 0 to infinity. Okay, so that's my domain and my range of a square root function. All right, now let's look at this last one here. So I'm going to say, what is the domain? All right, so there is a restriction. Remember, we can't have a 0 in the bottom. All right, so that means 2x minus 3 cannot be 0. So 2x cannot be 3, so x cannot be 3/2. All right, so I've got a split domain here as well. Okay, 3/2, not in the domain. Everything else is, except for 3/2. So we're going to have a split domain right in the middle there. And that's how you represent that the 3/2 is not in the domain. Okay, so let's just leave it at that for now. That's a good introduction to using set notation when you're talking about domain and range. So let's talk about increasing and decreasing intervals. So when talking about increasing, decreasing intervals, I'm talking about x values. All right? So when you're got an uphill slope, you're increasing. When you've got a downhill slope, you're decreasing. So remember, we're talking about left to right. So left to right, increasing, left to right, decreasing. All right? So let's do increasing first. So increasing intervals. All right? So let's see, I'm going uphill here. All right, then I'm going downhill here. And then I'm going uphill here. Okay, so I've got two intervals where I'm increasing. So from here, going that way, and from here, going that way. Okay, so negative infinity, positive infinity. All right, so the first piece, this one here, is negative infinity to 6. All right, we always use smooth brackets when we're talking about increasing and decreasing intervals. All right, so 6. And then I've got a 2-piece interval I'm talking about here, so I take up at 3 and I go to infinity. Always use smooth brackets when you're representing increasing and decreasing intervals in interval notation. All right, now let's talk about the decreasing intervals. All right, so decreasing intervals. All right, so let's move this. So now the decreasing part is in between. All right, so decreasing intervals start at negative. I forgot my negative on this first piece here. All right, so decreasing interval goes from -6. Let's see, I was using blue, -6 to +3. Smooth bracket, and there's only one piece of this function where we're decreasing. Okay, so what we've done in this video is given you a few examples of how we're going to apply our knowledge of interval notation.